Let's talk about combinations. Now, combination is a selection of items from a larger set where the order does not matter. Well, what is that larger set? That larger set is permutations, arranging every object in order. But for combinations, the position of the items is irrelevant. So we want to see the arrangements, but then disregard the arrangement. So how do we do that? Well, the combination formula gives us maybe some insight on how it's done. So here's the formula for calculating the number of combinations of n items taken r at a time. And you have this function notation, then you have this n choose r, and that's equal to this formula of n factorial. If you remember, factorial means n times n minus 1 all the way down until it's 1, and then divided by two parts. We have r factorial and n minus r factorial. Now this n minus r factorial, this n minus r is the objects that we're not selecting, and this r is the objects that we are selecting. So let's see if we can make some sense of it. So let's take a look at the example. Suppose we have 5 different fruits. We have apple, banana, cherry, date, and elderberry. What we're doing here is just using letters A, B, C, D, E, but let's think about it in fruits. So we want to know how many ways can we choose or select 3 of these fruits out of 5. So we can identify these parameters that n is equal to 5, the total number of objects, and r is how many are we taking at a time is 3. So let's apply this formula, is that 5 choose 3 is equal to 5 factorial divided by 3 factorial, and also divided by 5 minus 3 factorial. So I think in the video permutations, we explained why there was this 2 factorial in the permutations formula. And so this is accounting for the arrangements of the items that we're not selecting, which would create some repetitions of the objects that we are selecting. So that's for permutations, but for combinations, we also have to disregard the arrangements of the objects that we do select. And that's where this 3 factorial comes in. So we have 5 factorial is 120. This 2 is because the extra 2 fruits that we're not taking, because remember, we're only taking 3 out of 5, the extra 2 fruits at the end can switch orders, and that will duplicate the first 3. And so we have to divide that out. And where is this 6 coming from? Or where is this 3 factorial coming from? Well, this is the arrangement of the objects that we are selecting. So let's take a look at this 3 fruits selected from 5 fruits. There's 10 unique combinations. So these combinations are, you have all these apple, banana, cherry, apple, banana, date, apple, banana, elderberry, and so on and so on, so on. So there's 10 unique combinations of selecting 3 fruits from 5 fruits. Now, where did this come from? Well, if we were to actually arrange all of the 5 fruits, then we would say, well, this is just a straight 5 factorial. This is all of them, right? 5 factorial, of course, is equal to 120. Now, if we were only selecting or arranging 3 of them, but the order of those 3 did matter, then that we could say, well, we have an A, B, C here with a D and an E. And then in another arrangement, we have A, B, C, and then E, D. But if we cut the last 2 pieces off, we have this really the same arrangement, right? A, B, C, A, B, C. So that's why we're dividing by 2 factorial. So why the 3 factorial? Well, the 3 factorial in this combination formula, if we're dealing with combinations, we're not concerned with the arrangement or order of the objects that we do select. So we don't care that A came first and then B was second and then C was third. We're just putting it into a fruit salad. So it doesn't matter what the order is in which we've selected these 3. A, B, C is really the same, is no different than B, A, C or C, B, A. Those are all different arrangements, but we're not concerned with those order of arrangements. So really they mean the same thing. So there's this repetition happening of how many times you can arrange these 3 letters that you're taking. And that arranging 3 letters or these 3 fruits is 3 factorial. So again, reviewing how combinations are different than permutations. Suppose we want to choose 3 or select 3 items out of a set of 5, N is 5 and R is 3. But let's take a look here. In permutations, the order position matters. So apple, banana, cherry is a different arrangement than banana, apple, cherry. And so it would be counted as a different. So this is 1 and this is 1. But in combinations, apple, banana, cherry is not different than banana, apple, cherry. Of course, arranged differently, yes, but in combinations, we're not concerned with that order. So once we have counted all of these different orders, we have to cancel them out. And therefore, these ones would count as a repetition. And that's why we have to divide by the 3 factorial, the number of arrangements of the objects that we do select. So there's a key difference between permutations and combinations. Permutations count all the possible arrangements of our items, but combinations would ignore the order of the arrangement. So you can see in the formula that you would also have to divide by the number of arrangements of the objects that are selected. So let's take a look at an example then, after we look at these key points, of course. So order doesn't matter for combinations. Apple, banana, cherry is the same thing as cherry, apple, banana, and therefore you have these repetitions that you're going to have to make sure that you discount, that you cancel out. So, of course, combinations are useful in probability and counting problems, combinatorics, and they're talking about groups and sets rather than sequences or arrangements. Another key point is that combinations are always less than their permutation counterparts. So if you said that I'm going to arrange 3 items out of 5 and the order of it matters, that A, B, C is like a gold, silver, bronze, then that would be a permutation. But combinations would be that, A, B, and C, these 3 students place in the top 3. So that's that the order in which they place is not important. So that would be a combination. So let's take a look at this example. There's a grant offered to the school that pays for 3 junior high school students and 4 high school students to attend this leadership conference. And they're chosen from a student council that has 5 junior high students and 6 senior high students. So let's determine the number of ways to select the students for leadership. So I think we have 2 selections that we have to do here. We first have to select the junior high students from the pool of junior high students, and then we have to select the number of high school students that are going to this conference from the pool of senior high students. Okay, so let's first find the number of junior high students. So the pool has 5, on the council there's 5 junior high students, and we are going to select 3 of them. Again, we're using combinations now because there's no distinct special role out of those 3. There's not one that's a president and a vice president and secretary. We're just choosing 3 junior high students that are at the same level. They're going to this leadership conference. So 5 choose 3 is equal to, you could use the calculator, but let's just do it by the formula here. We have 5 factorial. We have 5 minus 3 factorial, which is the 2 extra ones. We have to cancel out those arrangements. And as well, we also have to cancel out the arrangement of the objects that we have. So 5 factorial divided by 3 factorial, 2 factorial. Let's just put that 5 factorial divided by 3 factorial, 2 factorial. And if we continue here, this 5 factorial is going to be 5 times 4 times 3 factorial. That's going to cancel out our 3 factorial. And also our 2 will cancel one of these 2 here. So this will cancel. And we have 5 times 2, which is equal to 10. So there are 10 ways to choose the junior high student. Now let's, for the senior high student, out of a pool of 6 senior high students, we're going to select, how many we're selecting? 4. We're selecting 4. So again, we can use this, we can use a graphing calculator, but we can also just use the formula here. We have 6 factorial. We have to account for the repetitions for the people that we don't select. So 6 minus 4 is 2 factorial, 6. So that's the extra 2 that are not going. And then we also have to cancel out the arrangement of the students that are going. So we have to do 4 factorial here. So continue that. We have 6 times 5 times 4 factorial divided by 4 factorial, and then we also have a 2 here. This 4 factorial will cancel, and this 2 will, well, remember that 6 is 2 times 3, so this will cancel out the 2, and we'll be left with the 3. In the end, this is going to be 3 times 5, which is 15. And since these are independent, we can multiply them using the fundamental counting principle and say that the total number of ways to select the students that are going to this leadership conference is going to be 10 times 15. So it's going to be 150 ways. So a little bit about the combinations and how they're different than permutations, and how an example of using combinations to solve a problem. Okay, I hope that helps you, and I will see you in class.